Thanks for coming, everyone. It's my great pleasure to introduce Matthias Felleisen here as our distinguished speaker for this week. And of course, I should put in the mandatory plug for our Wednesdays at 4 p.m. Do come back for lots of interesting speakers throughout the course of the year here. So let me tell you a little bit about Matthias. Yeah, next one will be in the fall, right? So make a note, yeah. So let me tell you a little bit about Matthias to introduce him. Matthias is, of course, everyone who comes along in these distinguished speakers is quite distinguished. So Matthias got his PhD in '87 from Indiana. He was a full professor 5 years later at Rice University. He moved on to Northwestern University in 2000, that's the what and where. His early career, he worked on essentially theoretical parts of programming languages research. So he was the first to crack the full abstraction problem, namely the problem of given a denotational semantics, can you make an operational semantics that matches it in a precise way? And this was, for the field of programming languages anyway, in computer science, a long-standing open problem. He also, one of the most widely used proof techniques was something that he developed in that early period of his career. So if you flip open a POPL or an ICFP, two of the top conferences in our field, you'll find about half the papers use his proof technique for establishing type soundness. And then kind of a strange thing happened. Matthias is he's a rare and curious bird. He, about halfway through this career, he just decided, you know what, this theory stuff is great, and I seem to be good at it, but I'm going to do something that maybe has a little more impact on the world. And he switched to education as his main focus, and of course, along with that, the more system building side of the programming languages research area. And so he's going to tell us about that and what's going on in that part of his research now. But one of the things that's happened as a course of this switch is that he's just this year won the Karlstrom Award, Teaching Award, which is the highest honor that the ACM bestows on teaching honor. So without further ado, let me introduce Matthias, and please give him a nice welcome.
Can you hear me? It's fine, okay. Well, thanks for the introduction. It's very embarrassing. Oh, nice. So teaching, I still consider my hobby, not my first thing. And I don't publish in education conferences. I really publish as a programming language and software engineering researcher, mostly about design. But it turns out that teaching is on everybody's mind who's in academia. And when my dean goes to the snowbird meeting that happens once a year in, I think in August or September, he comes back and says, we had the following agenda, but we talked about the first year. Because every chairman and every dean who goes out there wants to know how to solve that problem. So when I say first year, I mean this hobby project of Don't Teach Scheme, or Teach Scheme Bang, that I started many, many years ago. And first year could mean using programming in middle school or in high school, all the way up to the master's program, the professional master's program, where we teach it now too, to give these people a boot camp experience. And it really is about what do you do to get students on a solid foundation. So when my dean or your chairman goes out to Snowbird, what do they mean when they say the first year is a problem? I'm going to spend a few slides on that so we're on the same page. And then we're going to see what we do. That includes Robbie and me and 10 other students that are now professors somewhere else than me. So I personally learned to program as a 19-year-old in 1978 at a technical university in Germany. It's actually an MBA-like kind of program, but it doesn't matter. And what we learned was things like what you see, variables and assignment statements and printing things, hello world and arrays, loops. I actually saw classes in methods. Because in my first course, I learned Algo 60 and Similar 67. And so after about half a year, we did this. I had no clue what I was doing, but I used classes and I used methods, and it was great. So, and if you teach a programming course, if you look at any programming course in this day and age, guess what it does? Variables, assignment statements, arrays, classes, and methods. And if you're lucky, you get maybe interface inheritance. But otherwise, it hasn't changed. What changed is the syntax with which we deliver stuff. My own personal school went through 8 languages. My hunch is that they're on the 9th language now, because the current fashion is Python. So that in 30 years, in 30 years, 8 or 9 languages gives you an average lifespan that is shorter than a BS program. Right? So the average fashion that we deliver to our programmers is just that, fashion. We might as well be a fashion magazine. You open it, you throw it away. Right? Is that what we are about? Are we a science, or are we a fashion delivery vehicle? Can we do better? And the real question is, of course, when you deliver the syntax, how do you teach programming? How do you teach programming is, usually you introduce a bunch of syntax. That's what I meant with variables, assignment statements, loops. You show a bunch of examples, and then people generalize from the examples, adapt them. They do lots of those, and we pray secretly, not letting anybody else know, we pray to the various gods of programming that when they come out of the course, they know how to program. And we have failed for 40 years. We really have. Because that's not what we as an intellectual discipline are about. There's a lot more. We learned a lot in the 70s and 80s. We should put it where it belongs, in the freshman course. What I believe belongs in the freshman course is an idea, a theory, and a practice of systematic program design. That's the primary thing we should think about. We can use this in middle school to show kids how mathematics is an exciting delivery vehicle for video games. And they get excited about math. We can use it in the master's program to show them how to catch up from their underdeveloped BS programs, or BA programs, wherever they come from, and everything in between. And I'll explain to you what I mean by that. It's not quite independent of the rest of what you do. You will need a good programming language. My claim is, and I've cut that part from the talk, I'll get there in a moment, no existing commercial programming language or open source programming language, or whatever, any popular language, no language like this is good enough to teach novices. That's why the project that we run is called Teach Scheme Not. And when you are, if you're a Pythonista, or if you like Ruby or JavaScript, it should be called Teach JavaScript Not, because no language exists is good enough. Same is true for IDEs. Microsoft sells what's called a pedagogic version of Visual Studio. Do you know what it is? It's 8 bits that turn off 16 features in Visual Studio. That's it. That's not pedagogic. Of course, with all of that said, if you don't make it fun, you don't reach the hearts of the students. And you have to reach the hearts and the minds at the same time. You need to reach the minds for all the people who need to know that computer science is deep intellectual content. It is not the paper and pencil science for physicists. There's certain. So this is the picture. But I will do to Robbie what Robbie did to me. I had promised Robbie a talk on research out here, and he came in and did not deliver the first year talk that he said he would do. He delivered a macro talk instead. I'm delivering to you only half of my talk, because the other half, the green half, is what he worked on with me together, and he has a great talk on that too, and he will deliver it to you sometime later in the fall. So that was the beginning of his videos. Promises. I need to deliver you some context. So I'm going to speak from my own personal experience, but we have delivered this curriculum in several hundred high schools, in a few dozen middle schools, a bunch of graduate programs, and everything in between. But I'll deliver it from the perspective of, after I moved from a top 10 school to an average school like Northwestern, what is it like there? Setting up the context first and telling you later how it worked. Because I was told by a certain group there that scheme is for elitists and you will fail here. And the opposite happened. I can tell you that much already. Otherwise, I wouldn't be here probably. So what's the context? Like everybody else, our students go out early on and get jobs. The difference is Northwestern is a serious co-op school. Co-op means you have a 5-year program, 3 times 6 semesters, 6 months of those 5 years. You are interviewing for a job, you take a job, you have a mentor. We have co-op faculty in the college that communicates with your mentors, make sure that you're evaluated, you self-evaluate, you compare evaluations, you get diagnosed on how you performed on this co-op. We have co-op employees over the entire United States, and we are in a totally direct feedback loop. They tell you, when you're sending out 450 students a year, how badly they're doing. And by golly, they did. And so it's distributed, and the only free time our students have is the first summer. Everything else is totally planned out for them. So that's half of the story. Of course, what that means is that like everybody else, we have 2 critical points. Number 1, we have to get them ready for regular jobs here after 3 semesters. Now, it used to be 3 quarters. Now it's 3 semesters because we switched. And of course, we have to get them ready for the job. That's a bit easier for us than for you probably because the co-op experience is a tremendous mind changer. It also makes them buzzword compliant because at the end of the 5 years, or 4 years in your case probably, you have to make sure they can talk the buzzwords, they can act like software developers when they interview you for jobs. But here it's critical too. At the same time, we all know, if you've taken piano lessons, for example, you all know if you don't get the technique right, you don't get the principles done at the beginning, it's very, very difficult to get them in later on. Because when you acquire bad habits of design and programming, they will stick with you. It takes a near miracle to change, which is why we see a lot of bad code in the real world. And I was told about various websites where you can go and look at bad code, as if I hadn't seen enough already. So I believe that you need to figure out a lot of principle work here, and you slowly go over to something that's practical. And of course, that transition is true in the real world and in the 5-year program too. Mix and match. Keep going with principles, design principles, programming principles, systems development principles, but start bringing in things that students can use in the real world. As Alex Wolff said, our big colleague from the National Academy, the average knowledge of an engineer expires in 6 months. We are absolutely sure that ours lasts 2 to 4 years beyond graduation. That's a huge factor. So here's then the curriculum, and that's just a bit of what we did. We used to have a mathematics track that was borrowed from the mathematics department and logic department, and the fundamentals track which we taught. This is where we plugged in the original how to design programs component. This is what we developed later. It's called how to design classes, but it should really be called how to design components. I have control over the entire curriculum here and more, actually, downstream in the undergraduate one. This used to be in mathematics. We took it on our own. And for example, this second course in mathematics now is reasoning about programs. Because of this course, students write video games here and prove theorems about them with the same techniques that AMD uses to prove the correctness of code processes in your chip. Okay, that's first-year students because we enable them with the curriculum deployed here to be that far after 1 semester. So this is my focus now, the left-hand side, the design principles, heavily biased in this semester. This one follows automatically, you'll see. What I get from that is 3 things. I want systematic design, and I want a model of computation that explains everything. But if it explains everything, if it's for freshmen, possibly for freshmen in middle school, it can't use more than 7th grade algebra. And you can do that. So that's my little bias about the choice of programming language. It has to be as close as possible to 7th grade algebra plus more interesting data. That's, of course, the trick. In algebra, you do numbers. I want to do images, I want to do strings, I want to do all kinds of stuff. I don't want to do just numbers. But otherwise, it's that. So what does that mean? It means, really, as you probably know, pre-algebra equipped with functions that are possibly recursive give you a full model of computation. It's trivial, because all you need to know is when you have a function definition and you have a function application, you just plug in and you calculate with arithmetic. So algebra plus arithmetic gives you an explanation of video games. And students can really fall back on that to figure out on their own how it works. That's all I'm going to say about the computational model, because Robbie is going to talk about the rest later in the fall. But at the same time, you can turn it around. The amazing thing is, one of the trigger stories I had for this whole project was an out-of-body experience at Rice. At Rice University, the average SAT score for our class was the third highest in the country. We are behind MIT and Caltech. But even there, when I gave a little quiz in the mid-90s, about 10% of the students in the engineering school couldn't do basic algebraic problems. When you move to an average school in the United States, college, university, it's worse. I've had 5 students at the blackboard who couldn't figure out an area of a rectangle. Okay? So, another part of the purpose is, if you teach them how to build video games or graphical games, interactive graphical games, with plain math, they will also learn to use math in a second nature way, which is what you need in engineering school anyway, or in middle school, or whatever you deliver as the first year. So this is not just a one-way street, it's a two-way street. We computer scientists know way too little mathematics. I learned more mathematics in my business school undergraduate education than most average computer scientists learn here. I had topology, I had advanced back integrals, I was all in there. You don't see it anymore in our computer science programs, and we need it. Good. That's the pre-grad, that's the context. Now we go to the essence. The essence is this book, which I co-authored with Robbie and 2 other graduate students, but it's also free online. You don't have to buy it. And it's all about bringing design principles into the first course. So what are attributes of design? In my mind, there are 2 attributes you need to be able to deliver. Number 1 is you have to be able to tell students what the steps are so that they make progress. Measurable, small progress. That's step by step. Every design, whatever you call design, has to deliver something to students so it can make gradual progress. The other thing is, we are called computer science for a reason. What we deliver, the product that our schools deliver, is a programmer. A programmer is a mini scientist. He iteratively develops models of what he really wants to deliver. Nowadays, it's known as agile programming or iterative refinement, but it really is that idea. So those 2 things have to be an attribute of design. Next thing is, if I give you a problem and I choose a certain design strategy with a certain iteration, then you should have a reasonably canonical outcome. You should be able to look at the product and say, he chose this design strategy for this problem and came up with this program. If you can do that, you know that you have a strategy. If you can't, you have random advice. Random advice isn't bad. It works sometimes. But that's not what you want to teach in the first course. The last thing is, it's part of the reason why you want to do that. You want to think about design as something that's like a continuous function. When you change the input a little bit, you change the problem statement, like you add more information that need to be processed, you add a little different flavor of information, that change to the problem statement should lead you directly to a small change in the program's outline so that you know what to fix. And that's important because if you hand over the program to somebody else, he should be able to do that. So this continuity, this natural notion of continuity that we know from mathematics should apply to design. If you don't have those things, I wouldn't call it design strategy or design theory. Next thing is, why does it help? In the teaching world, it helps for two important reasons. Number one, there is no course for novices where novices don't get stuck. They come to your office and they say, I have those 3 pages of code and I get this dump and I don't know what to do. And what do? If you now whip out the debugger and you help them find the bug in the program, you have lost. You and your students have lost. Anything that's specific to their program that they do will not help them to overcome this problem when they have it again and again and again. You need to empower your students to solve these problems on their own. That means you need to show them a method that works independent of all problems, or of many problems. So it has to be, and our design SB does that. We teach it as a diagnostic tool to teachers, and we teach it as a diagnostic tool to students. They can self-diagnose how far they have gotten in the solution process, what they should do next, and what question they can ask, independent of the problem, of the teacher to help them guide through. That will demand a very different training from your TAs or your teachers. You can't throw your average first-year student into this course. He doesn't know how to act. He will blow it because he will whip out a debugger. He will not help your students empower herself or himself. It will just be wrong. That's an issue. I'll admit this. Industrial programming. A couple of years ago, I gave a talk at National Instruments. 200 people in the audience. Turns out 150 or 120 of them had taken courses from me. And then they took me through a tour of their labs. I was blown away that had actually transferred this knowledge into C++ programming, especially for MATLAB, LabVIEW. It's a programming language for instruments. Why do they do that? Because they noticed that no programmer sticks to the same project all the time. But if they follow a continuous design strategy, the next programmer can pick up where the previous one left off because he knows how he got to that point. Small changes here will give you easily access to the right solution changes over there. That's why it works for them, and it really works in many, many cases. So what is it then? In our world, in this blue book, we cover 5 areas of design. And I will focus on those abstractly first, for the rest, and then give you a concrete example for one of them, a couple of examples. First one is what we call structural design. You take the structure of the problem data to guide the process. The second one is generative recursion. It's the evil kind of recursion that everybody hates. But both are recursive. So what's wrong? We'll see. The next thing, of course, is the big savings of computer science is that we can abstract over designs and reuse them in a more powerful, richer way than any other engineering discipline. So we have design approaches for abstracting. Then there are 2 attributes. Sometimes you need more than plain structure. You need more knowledge. That's called an accumulator in our terminology. Sometimes you need state changes, because time plays an essential role in programming, controlling things in the real world. That's assignment statements. I'm not a purist. I will not just use pure math because I like it. I do so much with it. And then I have to say, OK, let's move assignment statements in. But bring them in when they matter. So my goal is to focus mostly on structural design and give you more of an idea of the other stuff later. This is the essence. This slide is the only one you have to take away from here. This is the essence of our design theory for structural design. It has 2 dimensions. What you see along this dimension is called what we call process. Along this one, you see data. What's data? Data is possibly atomic. And how did I come up with this? By the way, this is all informed by my own background as an algebraist. I worked on algebraic specifications. I worked on logic. This is theoretical insights from logic, but they happen to coincide with design patterns in the OO world. Data in that world can be atomic. Booleans are atomic. Characters are atomic. Things like that. You know them all. Next, you can enumerate. You want to take a big set like the reals, but you want to enumerate a few important ones. You have a bunch of colors. 3 are important because you're modeling a traffic light. Enumerate what's going on. Structures, you want to compose pieces of information. As you can see, by the way, I am using a little bit of scheme here, just a little bit. Hierarchies, you may have a composition, a layering of such complex pieces of data definitions. For example, the state of the world has both a position, which is already structured, and a string as a part of its description. That's hierarchy. You can have unions. You can take existing sets and just combine them together, like set theory. And you can have recursion. And in computer science, almost all problems are interesting because of recursion in the data. That sounds weird. Let me show you another example. Natural numbers. If you wish to think about natural numbers from a principle point of view, as opposed to the for loop works, just believe me, trust me, please, right? You know that natural numbers is a recursive data type. Okay? Mutual recursion. Oops. After 3 or 4 weeks, we show our students how to write routines that traverse file directories. You can't do that if you don't follow design discipline. We can because we do follow. This is typically material for 3rd or 4th semester. That's data. So you have an idea of data. And as I said before, my own guiding principle came from set theory here, but I would never tell students. It has to be practical. I'm telling you because you're a mature audience. There are a lot more forms of data, but they're mostly co-inductive as opposed to inductive. They're co-structural, not structural. That's beyond most computer science, so we'll not dwell on this here. How about the process, going from here to there? What does that do? When you read the problem statement, what's the first thing you want to extract? Tell people to read it and read it again? Extract nouns and verbs, like in the old world, it's the best they can offer there? No. You will have information that you need to process. That's what we are. We are the information processing world. Information needs to be represented in your chosen language, whatever language you choose, as data. One of those up there, description of data. So that's what you extract. And you illustrate with examples how data represents information and how information can be mapped into data. Then you understand what your problem data is about. The next thing is you need to figure out, distill down to 80 characters what the purpose of your job is. That works for small 10-line programs and big 100,000-line programs. You need a purpose statement. Examples. Before you code, before you do anything else, everything abstract has to be illustrated. You illustrate what you want to achieve, the purpose statement, which is a 80-character English sentence, with concrete examples. Of course, as you illustrate with examples, you, in your mind, work through how you would solve it. You get a better idea how your program can solve it. At this point, you're ready to take stock. You take all these elements that you've seen before, and you organize it as a program outline. The program outline is dictated by the structure of these definitions. That's why it's called structural design. So this thing is directly influenced by which of those things you chose. How does that work? This is what I mean by empowering. Every student gets an index card. The index card contains the process steps and 6 questions. 3 for the template and 3 for the coding. And what it does, it tells them to extract from the structure of the data description, English, the structured English description of data. From that description, you extract with 3 questions how to organize your program. And then there are gaps left. That's where creativity comes in, but not much most of the time. You code. Now you do what most people call programming. In our world, most programming is at most 10% of the actual work. And it really means that. You take the template, you add 10% characters, and you have a working program. And it almost always works the first time. And that's mind-boggling. That's especially true for students who have never had programming before. People with 3 years of AP programming, they struggle. They think it can't possibly be that short. And then they're blown away when the girl who never had any programming in high school and is in fine arts, for heaven's sake, solves it with 10 lines of code. Okay? How does it work? Again, 3 questions that students can ask themselves. And when TAs encounter a student, they ask, how far did you get here? These 3 questions, again, of course, fill in simple conditions, fill in this and that, specifically targeted without looking at the problem. Okay? And then you test. Of course, what that means is turn these examples into what's called a unit test suite. This is the process. So now you have these 2 dimensions of structural design. And every design will comes with a grid like this. And what you see then is that there is a part where we computer scientists contribute to the problem-solving skills of students, and there's a part where we don't. If, as I say, the structure of these data descriptions determines the outline, the layout of your program, and all these steps influence this step, and this step then influences these 2. There's obviously one step where you can't possibly do that, or one place, here. This step says atomic data. Atomic means there is no structure, there is no organization to the data definition. So what does that mean? That means that when you write numeric programs, plain numbers, for example, Pascal triangles, factorial. Factorial is actually different, but you are sitting here with domain knowledge. The problem-solving skill does not come from computer science. It comes from the domain of where you solve it. For example, video programming, video cutting, or the numbers theory, or accounting, or whatever you apply the program to. Okay? The sad part is that a lot of programming courses focus on just those things and confuse problem solving that computer scientists can do with problem solving that engineers or accountants or artists can do. We should get away from that. You can do this for abstraction. You have a similar grid for abstraction, and this is where the big difference comes in what language you choose. So in our world, as I said before, the context is we have 2 courses that focus on design. The first one uses a functional programming language, a scripting language, really. The second one uses a heavy-duty type OOP programming language, also called Java. And the big difference does not come in anything but the abstracting designs. Functional programming means you use functions to abstract. Object-oriented programming means you use class hierarchies to abstract. And if you follow through, you actually fall on your face. But that's a different story. Because the problem is that things are not really designed well enough in most OO languages. Generative recursion is a completely different ballgame. This is where you do not exploit the structure of the data to drive your design. You have an a priori idea of the solving process. It's actually, in some ways, comes from the domain, too. OO has a tremendous problem picking that, and all they offer you is the command pattern. So if you happen to know about the Gang of 4 book and all this stuff, this is what they offer you. That's all. 1 out of 23 patterns. We can do better because we have a grid like this and a process that takes students all the way to proper design. Beyond design in these 4 things, you can have all those 4 designs with attributes. So each of those previous 4 design thingies can come with a strong induction meaning really structural design with more idea about where you came from, or stateful programming with assignment statements. We bring this into, we're running short of time. Okay, last thing, iterative refinement. Let me show you an example of a programming problem that's typical for our 5th, 6th week. It's not always that, we have a bunch of these things. Suppose you want to model a file system in your freshman course, 4 to 5 weeks into the course. You can't do that if you don't use a proper approach. What you do is you start out with files that are just strings, and directories are lists of files and directories. So there's some recursion in there. But as you all know, this is just an approximation. What we really want, of course, is directories have names. So you make a directory and you give it a name. You equip the model. You redo your model. You make a small change. And because design tells you how the organization of the data changes the layout of the program, your students know immediately how to do that extra little bit. But that's, of course, just an approximation. So you go on and you say, oh, files have names, and they have sizes, and they have dates, and they have list of characters. You make small changes. Another small change here. Because students have a design recipe that tells them if the data changes here, your program layout changes there, it's no problem for them to design this problem. They solve this problem. They have recursive walkthrough programs through recursive directory structures in the 5th week. You can't do that otherwise if you have design. So that was the theory. It was my purpose statement of what I want to do. I will illustrate this with a couple of examples. I will start out with how we get fun. You see the rocket fly? That program is the first program in the first lecture that we do with our freshmen in a college level course. Let me show it again. There's the rocket. That's our Hello World program. How does that work? It works the same at college level and middle school level. So this is part of our how we get kids hooked on math without telling them it's math. What you do is you start with the typical algebra problems. Horse buggy leaves Pittsburgh, trying to travel to Chicago, crashes in Philadelphia, and what time does it spend between there and there? Something like that. You know, your algebra book kind of things. And if you're lucky, you've trained your students to say the horse buggy travels at 10 miles an hour, so after 2 hours it's 20 miles, 3 hours it's 30 miles. That's fast for a horse buggy, I know. And you can tell the students that this means the distance traveled depends on the time, and it's 10 times t, plus a constant maybe. In our beginning student language, we can easily write these things like this. It's a little bit of scheme. Right? It's scheme EOS algebra. And it's not scheme that we use anyway. It's a small teaching language that's modeled on scheme. Because scheme, Python, Perl don't work. You don't want to work with numbers the first time around. Instead, you want to say, let's make a little video. Let's simulate, let's animate a rocket flying, taking off. Okay? And you say, instead of tabulating the distance traveled, you tabulate where the kids should draw the rocket. And I just made up random pictures here, but that's close enough to this thing. And there's a little lie in this program, but it's really small. And you figure out, just like before in algebra, they figure out a function definition that does that. But they're manipulating pictures, so it can't possibly be boring math. It must be interesting, right? That's how we hook the middle school students. That's the fun part. First lecture in college. Entire hour, 45 minutes. And all it takes then is to say, animate this function. Because the function takes a time and delivers a picture. And what does that mean? If you do lots of those, maybe 28 per second, you have an animation. So all we have to tell the kids is that this animate is a very fast function. It takes use and applies to 0, 1, 2, 3, 4 through 28 in 1 second. And then it goes on thousands of times, and you see the rocket fly. And everybody has the computational model at her fingertips to figure out how it works. Everybody understands the function. And we got them hooked. We go from there. We got them hooked at the college level, we got them hooked at the middle school level. And then at the very end, after 9 weeks of post-middle school, after school program, we tell them, you did math. That's math? It's interesting. How come I was bored in math? Right? But that's domain knowledge. So far, we have used algebraic knowledge about things. We didn't exploit structure. Let me show you how to exploit structure. This is a program from about 4th and 5th week 2. You have a shape sitting here, and you see this little mouse click moving around. The problem statement is, oh, wow. You have a shape, a complex shape on your screen, and it's actually from a DARPA programming contest where it came from. And you want to figure out whether a mouse click or a rocket hit is in this shape. Okay? So what are shapes? After some reading of the problem statement, you figure out the shape. This is the problem. So you extract this. It's either a square or a disk, or maybe it's one shape layered on top of another shape. And if you look carefully, you see recursion here, because you have structures over one shape over another, and you go back to shape. So this data definition, this is the data description, says I have two simple clauses, squares and circles. We all know how to represent those as data. But we also have this over shape, which combines two shapes into one. This is arbitrarily complex shapes you can make now. Well, arbitrarily complex over disks and in squares. And you have to show me what it means in information, okay? I didn't spell it out, but this is the example part of this thing. So if you do that, you set out examples and you have students interpret with little drawings, back of the envelope sketches, what it means. Or you give them back of the envelope sketches of shapes and mouse clicks, and you say, what would that be represented as data that matches the data definition? Okay? Step 2. The purpose statement is very easy. I give you a shape, I give you a position of the mouse click, and I want to know whether or not this mouse click is in the shape. So clearly the result is a Boolean. And there's a very simple English statement that explains what it is. And then I write down a function that is clearly wrong, but delivers a result that matches false. Okay, step 2. Step 3. Step 3 says, take your data examples from the first step and use them to explain what your function is expected to do. So for example, I can say make position at 45, the coordination point 45, 45 is in shape T. Well, T is here. It's two shapes, S and C. And I have to explain to my TA that it's in T because it's only in S. But that's good enough, because T is a combination of S and C. Right? So you went through the mental process of telling me how you would solve the problem. You are a step ahead in figuring out what's going on. We also reformulate this immediately as unit tests. So now they can run the program, and they will see actually sometimes it works and sometimes it doesn't. That's good. Step 4, that's the critical step. And I will demonstrate to you how these questions work. I've chosen the scheme syntax here. It will work exactly the same in Java. When you have a data definition with 3 clauses, your program that consumes that must distinguish these 3 kinds of data. That also means I need to have predicates that tell me whether I'm in the square case, in the disk case, or in the over case. Next question that students can ask themselves to empower themselves, be independent of the teacher. Where is the recursion? Right here. Okay? Or where is the structure? What else can you select? And now you indicate with a little function call that this is, just like in the data definition, self-referential, recursive. There's other 3 questions. They ask them many times, and I can do that blind at 3 o'clock in the morning. Now you can fill in the code. You can fill the template so it actually becomes a program. The layout corresponds to the structure of the data definition. The code only fills in gaps. For example, you start with the empty, the cases where there is no extra stuff anymore. And here in this case, of course, you say, I'm going to give a wish list. I wish I knew how to write a function that tells me whether a point is in a square or a point is in a circle. And where does this knowledge come from? It's now atomic. So it must be coming from domain. What's the domain? Geometry. You can tell the students where to look. Go to your geometry expert and figure out how to do that. I know we look in the geometry book if I can't remember. But here, in the 3rd case, you have stuff lying around. You have information lying around that you should exploit. How to exploit this? You remind yourself what these things already compute. This computes whether you are in the top shape. The next thing computes whether you're in the bottom shape. If you're in either one of those, you are inside. The point, the mouse click, is inside that shape. So all you have to do is combine those two. That's what I meant by the template, which is designed by asking questions, is 90% of the code. Only OR and these two functions have to be added. So when students are stuck in this process, you don't have to say, let's think about shapes. You can say, where are you? Diagnose whether they have a domain problem. Maybe they were sick on the day when people dealt with domains like squares and circles. Or maybe they have really a problem of getting the program done. So now you test, last step. And this is a glimpse at one of Robbie's marbles. Of course, the IDE, a pedagogic IDE, has to tell you whether your unit testing is good enough. In this case, it tells me, I didn't cover that part. My examples are not good enough to cover this part. It has to be built in for novices so that they know testing and example making is not just a silly little exercise. It's critical. And we tell them you have a bug until all these things are gone. All these black spots are gone. When you wire it all up, what you're doing is an event-driven programming model. And some of you have seen that before. You just say you create an operating system, which you call Big Bang, and you have callbacks for mouse clicks, and you draw it, and it's all working out. Again, I'm a little bit short here, so I'll just tell you this works in Java just as well. You do interfaces, you use classes, and what it is, it turns out, if you look at these theoretical principles and the results they deliver, you will find out that it's exactly what the design patterns would tell you what to do. Design patterns are based on software archaeology, so they're empirical evidence that this design theory that I've developed is giving you the exact same results, good results, that survive. Problem is that all programming languages are ill-designed. I could give you an entire other talk. I gave a keynote at an object-oriented programming language conference on why that is. It has nothing to do with education. This is about research again, so I'm skipping this part. Okay, last 10 minutes. I'll give you a bit of an evaluation. How well does a curriculum work that's not based on fashion, but based on rigorous, deep principles of design? We have evaluated a whole bunch of things. We have put together a package, of course, that delivers this design recipe with a fun part, a pedagogical IDE, and so on. Robbie can talk about this. We have evaluations that high school level. We rigorously evaluated the rights introductory students. So I'll give you four of those things real quick. But I will tell you, in my experience, people who are set in their mind to teach an old-fashioned course will ignore all evaluation. So which is why we don't publish evaluation data. We have very, very good data. But we have found time and again that people who are dead set on teaching an old-fashioned conventional programming course will not be swayed by our data because it's not applying to their situation. So I'm giving you a bit of information, but it's not to convince you. It's just to give you an idea of what I personally think we can do with this based on the anecdotes that we have. So the first test we did was an independent evaluator at Rice, was hired by NSF to look at one teacher in the same school teaching 3 different classes. 2 were in the curriculum that's called AP C++. It was 1996. The third one was our curriculum. The amazing thing was that over all students, there were approximately 70 or 80 students in those 3 classes. 70% preferred HCB. The more, so they mixed. In this class, they showed 2/3 C++, and then our curriculum. Here they showed our curriculum, then 1/3 C++. The more C++ they showed, the more they hated it. It's not surprising. The amazing thing is, which is what we cannot explain to this day, we have conjectures, but we have no explanations, is that females in this group, this is half female, half male, preferred our curriculum by 4 to 1. not by 4%, by a factor of 4 to 1. That's high school. We have trained, at the time, we had trained 300 high school teachers over 4 years. We then, NSF hired a company out of Cambridge in Massachusetts to validate the high school teachers' perception of that. And 95%, close to 95%, told this company, this curriculum changed my mind of what computer science is and what it teaches to students. That could be detailed in details, but that's not very important here. Second evaluation scenario. Rice did not take well to the SSCP approach, which I had to teach in the early 90s. Especially electrical engineering thought that it was going wrong. So we switched. We went out to design programs. Electrical engineering designed its own C++ and Fortran. It was the second course. Introductory curriculum for computer engineers. And we split up. They no longer required our course. They did their own. They actually assigned an award-winning, a local award-winning faculty member, Don Johnson, you may know him, to this course, and hoped that that would convince people to come to theirs. Then these students went into the same C++ course second semester. So these people saw an entire year of C++. These people saw a teaching language that is roughly like Scheme for one semester, and then went to C++ for the second semester. This course was taught by the systems group at Rice, people like Alan Cox, Alejandro Shaver, and people like that. And they came to me, even though they were very skeptical about my approach, and said time and again, it's mind-boggling that your how to design program students are better C++ problem solvers than the people who went through the C++ course already. So that was the second evaluation scenario. Northwestern. I moved to Northwestern knowing quite well that I was going from a top 10 school to a top 500 school, or something like that. I don't know what it is. And the amazing thing is that they had Co-op, they sold Co-op as this big attraction. And students went out on their first Co-op, and two-thirds of them got jobs moving machines, plugging cables, and running scripts that they could never read. That is, for a tuition cost of, at the time, $160,000 for the 5 years. That was before my dean at the time asked me to take over the first course as an experiment. And the associate dean telling me, you will fail because it's for elitists. Now we have the opposite. 3/4 of our students pass the interview process with flying colors and actually get a programming job on the first Co-op. Because of the tight feedback loop between our Co-op department in the College of Computer Science and the Co-op employers, we know how well they do. The worst part that happened was that the Co-op employers bitterly complained that our third-year undergraduates, we call them middlers, are actually better programmers, better designers than our 6th-year master Co-op students. And so the associate dean asked me to collapse my 3-semester curriculum into a 1-semester MS boot camp. I've been at it for 2 years, and we're slowly changing things. Fourth evaluation scenario. So we took it up from the college level to the master level to the high school level, now middle school. Starting about 4 or 5 years ago, a group of volunteers from our school, undergraduates, decided to go into local neighborhoods and teach middle school students. A national outfit called Citizen School, who employs volunteers called citizen teachers, comes from citizen soldier, to deliver after-school programs through scripts. They have no clue, they're not domain experts, they read scripts off to students, so to speak. Asked us to whether we could try shoving it into this program. We did. This is an explanation this is the one slide from an international talk. So American system, middle school. We go in here, we deliver this. We have taken over schools in Harlem, 2 schools in Harlem, a school in East Palo Alto, suburb of Austin. It's also very poor schools, very poor districts, very poor scores. We have kids who fail mathematics and who come out of this going back and pass the state math exam. And teachers are blown away. They call up our coordinator, it's a Harvard education school student, and they call him up on a regular basis. I think he gave a talk here a couple of weeks ago. And he said, what did you do to my students? Well, we just taught them how to video program in mathematics. Of course, teachers can't do that. The average teacher doesn't know how to do that. It works like a charm. We only have like 10 schools. There's not much more to say, except that we have anecdotal evidence. We are now preparing a systematic evaluation of scores, of how we lift these kids' scores, because we have some preliminary indicators that it works really well. So the successes are reasonably obvious. If you use a systematic design process to teach your freshmen, you and your students will benefit. You have a diagnostic tool. The students have a self-empowerment tool. Our students, by the end of the first year, get stuck like your students, but they know how to make progress with their design recipes. They actually challenge our assembly language instructors to follow the design recipe. That was a real success. We give fun in good doses because you need fun to reach students' hearts. But fun should not be the primary thing you teach in the first course. It should be the ingredient that convinces them this is really good stuff to know. And when I say good stuff to know, time and again we explain, I personally explain, and other teachers explain too, how to apply the design recipe to journalism, medicine, proofs in geometry, you name it. Because it works there too. I give personally concrete illustrations of that. Others leave it abstract. And we have students tell us, I took 1 year of computer science. I didn't want to major in it, but it helped me to do my journalism assignments. That's a success. That's over here. We have failures. Time and again, I encounter people who hate parentheses with a deep passion. I'm sorry for them, but it's actually my problem. Time and again, we realize that this curriculum is requires a wholesale adaptation. You can't, unlike other curriculum innovations, you can't make a small change to your course and import 1 week of that or 2 weeks of that and leave the rest alone. It doesn't work. You don't have the programming language that empowers students. Very few programming languages are good enough to empower you to get there. You don't have the IDE support, but you also don't have the curriculum support. Just because your programming language is Turing complete, and you should be able to solve this problem, does not mean the design recipes you have taught so far actually do so. You've changed from just because it's doable, to it's doable in the right way. Again, I have an entire talk on the expressive power of programming languages, a research talk, that is trying to undermine Church's thesis. Because Church's thesis is useless to computer scientists who actively practice software engineering. But that's a research talk. So, conclusions. One more slide. I'm done. It's 5 o'clock. I have to be done. What I'm telling you here is computer science doesn't have to sell itself as a fun thingy or as the paper and pencil administrators for physicists and biologists, whatever. It can do a really good job selling principles because it's doable with fun. It's effective because you teach good problem-solving skills. It's productive because industry practices helps too. And I think it's the right thing to do to show us that we are real science. We're not just a little side discipline. What you need to do that, if you're thinking you could do it in Perl or Ruby or JavaScript, you need design principles. Most of them, what I've shown you, work in almost all languages. I can personally work in assembly. To do it well for beginners, you will need a teaching language. I don't think any language works, and that includes Scheme. My own personal shocking insight was that Scheme was a bad idea for beginners. I nearly cried when I saw how bad it was with a student with a perfect SAT score, 16 SAT score, a son of a physicist, a colleague, who just couldn't believe he had misplaced one parenthesis, And it destroyed his self-confidence to the point where he cried. That's scheme to you. And you know what? Give me a programming language, and I will do you the same thing. Every programming language is out there. You need to restrict it to the teaching language and build up the confidence over a semester until it's right. The third thing is you need a pedagogic IDE. Something that makes life good, that scales to software engineering if you need to, but that also knows that a novice is a novice. And novices make one thing above everything else. They make mistakes. And mistakes you should recover from mistakes gracefully, not by brutal problems. Those two parts I didn't show you, but as I promised, Robbie will give you a talk on that. All of these belong together. We call them the Trinity. It shows my Catholic background. But it is the Trinity of things that we believe really worked and got this delivered to everybody. We spent about 10 years with 3 to 20 people developing this. If you want to go for it, good luck. Thank you very much for listening.